definitely ask me about. So here's the first problem. F of theta is equal to 12 cosine of theta plus 6 sine squared theta. And although this problem isn't the same exactly, it is very similar to the discussion problem that I think Carla posted yesterday. So this definitely has a similar kind of answer, although not quite the same. So I want to find the critical values of this function. So critical values and classify. So when someone says classify the critical values, they just tell me if it's a maximum or a minimum or neither. And I'm probably going to, I didn't see this written in the problem, but I'm probably going to assume that this is limited to the interval from 0 to 2 pi. That's a pretty typical interval when you're dealing with trig functions, although not always. Okay, that's fine. Yeah, if you guys, I mean, if you ever need it, basically like as far as attendance, if you attend for like 15 minutes, you're going to get marked here, right? I think once or twice I've not marked someone present because they were here for like 2 minutes. But if you need to leave early, that's fine. If you come late, that's also fine. You're going to get marked present unless you came for like under 5 minutes. Even then, most of the time they usually mark people present. That doesn't mean you should just, right? I mean, you should come and stay as long as you can, obviously. So let's find the critical values. Take the first derivative. F prime of theta is equal to, that's going to be negative 12 sine theta. And then the derivative of 6 sine squared theta is going to be, let's see, so when you take the derivative of sine squared, you're going to get 2 times your function times the derivative of your function. So you're going to get 6 times 2, so 12 sine theta to the first power times the derivative of sine theta, which is cosine theta. And we're going to set that equal to 0. Technically, we're seeing where it's 0 or undefined, but sine and cosine are both always defined everywhere. So there's no worries about this being undefined. All right. So whenever you're solving, whenever you're finding critical values, you really just want to factor. Right? I know it might be tempting to like add 12 sine theta over here and then divide both sides by 12 sine theta. And although you'll find some of the critical values that way, you will lose some of the critical values. So that's usually dividing by a variable is a really, really good way to miss some of the critical values. So you don't want to divide by sine of theta because you'd be losing a variable. So instead, we're going to factor out a 12 sine theta. So I factor out 12 sine theta. I'm left with a negative 1 here and a plus cosine theta here. All right, so what am I trying to do? Trying to see where this whole thing equals 0. So I'm trying to see where either this part equals 0 or this part equals 0. So I'm looking for where either sine of theta is equal to 0 or where cosine of theta is equal to positive 1. And if I limit myself to the unit circle, so I should be a little extra careful here. If I limit myself, limit myself to 1 revolution or 1 period, I'm usually, and so this is going to get a little slightly technical here. If they said that this was the interval, usually they don't actually say this is the interval. Usually they say this is the interval. You start at 0 and you go all the way around, except you don't get to 2 pi because 0 and 2 pi are coterminal. They end at the same spot. So usually you say this or this, but not both. So if I was looking for answers here, I would say, okay, well, I know that cosine of theta equals 1 when theta is equal to 0. And also 2 pi. But I wouldn't say 0 and 2 pi because there's kind of essentially, they're not the same angle, but again, they're what's called coterminal. Sine of theta equal to 0, you also get 0. And then you also get pi. Right? Because if you're looking at the unit circle, right, you're getting this point here where cosine is 1 and sine is 0. And you're also getting this point here where sine is 0. So 0 and pi. So I'm gonna, since I'm not sure exactly how the question was written, I'll clarify. If it was written this way, where the period or the interval was from 0 to 2 pi, our critical values would be theta equals 0 and theta equals pi. However, if they just said find all the critical values and you weren't limited, you would get every multiple of pi. 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, etc., etc. Right? Because any multiple of pi would give you sine equal to 0. And then some of them would also give you cosine equal to 1. The harder part maybe here is actually classifying these critical values. So if I'm going to classify these critical values, I'm going to write this on the other side. So my derivative is 12 sine theta. And then it was what, 1 plus cosine theta? No, negative 1 plus cosine theta. So you do have the option of using the second derivative test to classify them. I don't recommend it, right? We talked about this last time. It's usually not the way you want to go. I want to really use the first derivative test, which is just drawing the number line and putting all my critical values on it. Now, yes, there are technically an infinite number of critical values here. So right, I've got 0, and pi, and 2 pi, and 3 pi, and it just goes on and on. And I've got negative pi, negative 2 pi, okay. So the idea here is that you want to, you always want to pick something between each of your critical values. So I'm going to pick pi over 2. And I know that sine of pi over 2 is 1. And I know that cosine of pi over 2 is 0. So I'm going to get 1 times negative 1, which is going to give me a negative number. So between 0 and pi, it's going to be negative. Between pi and 2 pi, well, so let me actually say something here. Negative 1 plus cosine is always going to be negative. Right? We know, or we should know, that cosine of theta is always less than or equal to 1. It's also always bigger than or equal to negative 1. If we add negative 1 to each part of this inequality, or subtract 1 is another way to say add negative 1, we get negative 2 less than or equal to negative 1 plus cosine theta less than or equal to 0. So this part here is always negative. So then we can determine the sign of our derivative by just looking at this part here and knowing when is sine positive, when is sine negative. Well, we know sine is positive in quadrants 1 and 2. We know sine is negative in quadrants 3 and 4. So when sine is between 0 and pi, it's positive, which means the whole thing is negative because this part's always negative. When sine is between pi and 2 pi, sine is negative, so the whole thing's positive. So it looks like, I'm going to sneeze. Take that. Like I'm about to sneeze. It's going to feel good. You're going to get the sneeze out, and it goes away. It's because I looked at the sunlight, kind of, and you know that's the way to stop yourself from sneezing. So anyway, it looks like when we're on top, it's going to be negative. When we're on the bottom, it's going to be positive. And it's going to keep doing that. So it's decreasing, increasing, decreasing, increasing, decreasing, increasing. So it looks like we have, if I was, ooh, that was loud. We have that, we have a relative maximum at 0 and 2, right? So there, and there, and right there, at every even multiple of pi. The relative maximum at, I would say, x equal to 2k pi, where k is an integer. Every even multiple of pi gives us a relative maximum. We have a relative minimum at x equal to every odd multiple of pi, negative 1 pi, positive 1 pi, 3 pi, 5 pi, etc. Right? Because we're decreasing, increasing, decreasing, increasing. So the way we write that is we write it as 2k plus 1 pi. Again, where k is an integer. So that's what we would get. We could also use the second derivative test if you really wanted to. I really don't want to, but right, if you took the second derivative here, stop erasers. Took the second derivative let's see, derivative of negative 12 sine theta is negative 12 cosine theta. The derivative of this, you have to use the product rule. So it would be 12, so derivative of sine is cosine times cosine, so cosine squared theta, and then sine theta times derivative of cosine is negative, so sine theta is negative sine squared theta. That does not look like it's going to be fun to try and evaluate each of my critical values, right? So I do like f double prime of 0, that's going to be negative 12 plus 12. Oh, so this is a perfect example of why the second derivative test is terrible. If I plug in 0, which is a critical value, right? And we totally know that we have a relative maximum there from the first derivative test. If I plug in this critical value to the second derivative, I'm going to get negative 12 because cosine of 0 is 1, plus 12 times cosine of 0, which is 1, minus sine of 0, which is 0. So I get negative 12 plus 12, which is 0. And when the second derivative is 0, it means we don't know anything about the critical value from the first derivative. It could be a max, it could be a min, it could be neither and end up being an inflection point. So a great example of why we don't really like to use the second derivative test. I will tell you though, yeah, let me just do another one just to kind of point something out. So let's say we did, just for fun, we decided let's just test pi as well. So we know that cosine of pi is negative 1. Negative 12 times negative 1, which is positive 12. And cosine of pi is also negative 1 here, but cosine the negative 1 squared is positive 1. So I get 12 times 1, which is 12. And sine of pi is 0. So this ends up being 24, which is greater than 0. So that means that the second derivative test will tell us that we have a relative what? A relative blank at x equal to pi. Well, so what I want to stress here is that it's easy to make a mistake using the second derivative test, right? If the second derivative is positive, that means we have a relative minimum. Right, it's a relative minimum because the second derivative is positive means you're concave up, so you're opening upwards, and the critical point is at the bottom of that opening upwards part. So yeah, if your second derivative is positive, it's easy to think, oh, positive means max. No, not here. Second derivative being positive means you're concave upwards, means you have a minimum. So yeah, just remember, if you do decide or have to use the second derivative test for some reason, that think about concavity, right? If your second derivative is positive, you're concave up, you have a minimum. If your second derivative is negative, you're concave down, and you have a maximum. Okay. Let's look at some more examples. So typically, what we kind of do with all of this first, second derivative stuff is we basically use all of it to draw and make more detailed graphs. Is one, I mean, there's lots of things you can do, but that's one of the things. So let's look at this next example. Let's say I want to graph. And now when I say the words graph, I'm going to mean find the y-intercepts, find the x-intercepts, find any asymptotes, vertical, horizontal, or even slant. Find all the first derivative things, which means increasing, decreasing, and where you have a relative max or relative min. And second derivative things, meaning concave up, concave down, and where you might have an inflection point. There's kind of a lot of things to look for when someone says the very innocuous word graph. So let's graph f of x equal to negative 4x cubed minus 8x squared plus 1. The nice thing about this polynomial is we know there's no asymptotes. Polynomials where you have just positive powers of x added or subtracted together, no vertical, no horizontal asymptotes. So the y-intercept is going to be, let's see, when x is 0, f of 0 is 1. X-intercepts might be a little bit challenging here. X-intercept, if I set this equal to 0, yeah. Sometimes people make up things that don't have very nice x-intercepts. I might come back to that. I don't know if it's factor, right? When you have something cubic, it can be hard to see how it factors or if it factors. I'm going to leave that alone for the moment. We know there's no asymptotes. Let's look at the first derivative stuff. So f prime is equal to negative 12x squared minus 16x. Set that equal to 0. Again, you know it won't be undefined because polynomials are never undefined. I'm going to factor out a negative 4x. I'm left with a 3x minus 4. So I'm getting either x equal to 0 or x equal to, let's see, 3x equals 4, so x equals 4 thirds. So on my first derivative number line, I've got 0 and 4 thirds. And I'm just going to pick numbers that are not those numbers, right? You have to pick something that's not your critical point to plug in. So pick something like 6. Plug in 6, you get negative 24 times a positive number, so it's going to be negative. Plug in 1, which is between 0 and 4 thirds. Negative 4 times negative 1, which is positive. Plug in negative 1, you get positive 4 times negative 7, which is a negative number. So it's decreasing, increasing, decreasing. I will say, I don't actually write the intervals of increasing or decreasing unless asked to. But right, so we could say that it's increasing on the interval from 0 to 4 thirds. It is decreasing on the interval from negative infinity to 0 union 4 thirds to infinity. But again, you only really need to write that out if you're specifically asked to. Usually drawing this first derivative number line is good enough for a lot of the time. We do have a relative minimum at, is it at 0 or is it at 4 thirds? Yes, it is at 0 because we are going down to the left and then as we come from the left and then up to the right. So we went down, up, it's a relative minimum at x equal to 0. And we should also include the y coordinate because we're going to graph this thing. And y equal to 1. Now 4 thirds is going to be kind of gross. But at 4 thirds, we do have a relative maximum. So we have a relative maximum at the point x is 4 thirds and y is what you get when you plug in 4 thirds. If I'm short on time on a test, I would write f of 4 thirds. And then if I had time at the end, I would go back and figure out what that was. We can figure it out, it's just not very nice. So let's see, if we plug in 4 thirds, we get negative 4 times 4 thirds cubed. 4 cubed is 64. 3 cubed is 27. Minus 8 times 4 thirds squared is 16 over 9 plus 1. This is not particularly fun to calculate, but we can, yeah, I guess we can calculate. So 4 times 64 is negative 256 over 27. I might multiply this by 3 over 3 and get minus 16 times 3 is 48 over 27, but it's really 8 times 48. And plus 27 over 27. Yeesh. Yeesh. Okay. 8 times 48 is what? I don't know, 396? No, it's 320 plus 64, which is 384. So this is getting out of hand, right? We just say it's some number. I would probably leave it. I do. So here's what I do see. I do see that it's fairly negative, right? I've got, this is close to negative 10, right? It's almost negative 270 over 27. This is, I don't know, negative 16. So it's like negative 10, negative 16 plus 1. So it's pretty negative there. Maybe negative like 25-ish. I'm just writing that down to help me graph it. So that is one of the things that can be kind of gross when you are graphing problems like this, is that sometimes the y values of your relative extrema or your inflection points can be kind of nasty. Let's go ahead and look for inflection points. So we'll take the second derivative. Here's my first derivative. My second derivative is going to be negative 24x minus 16. So my second derivative is negative 24x minus 16. So that equal to 0. Here you can just solve for x because you've just got one x. So negative 24x equals 16. X equals 16 over negative 24, which reduces to negative 2 thirds. So draw the number line for it. Here's my second derivative. Pick a number larger than negative 2/3, like 0. Plug it in, you get 0 minus 16, so it's negative. Pick a number less than negative 2/3, like negative 1. You get 24 minus 16, which is 8, which is constant. So it's concave up, concave down. We do have an inflection point at x equal to negative 2/3, y equal to f of negative 2/3. Right? Because again, plugging that into the original thing is going to be not much less terrible than plugging it in there. So let's try and graph this. Let's see what we've got. So I now have my y-intercept at 0, 1. And I know I have an inflection point at negative 2/3 something. And I have, yeah, this one's kind of hard to graph. I'm not going to lie. We have a critical value at 4/3, comma. Oh, sorry, we have a relative minimum there. So we do know a couple things. So we know that it's going to be going like this. Right, a relative minimum there. And then we also know that over here at 4/3 we have a relative maximum. Did I do something dumb? Sorry, I'm just trying to make sure that I didn't do something dumb. So here's the issue I'm having. I know it's a relative minimum at 0, 1. Right there, relative minimum. But then at 4/3, which like x is 4/3, like right there. When I plugged in 4/3, I said I was getting something very negative, which I should be getting. Which means I should be down here somehow, yet still, but it's, what kind of dumb mistakes am I making? It's decreasing, increasing, decreasing. Did I make a mistake when I made this sign chart? Let's check. So I picked something larger than 4/3, like 10. It's a negative times a positive. Did I make a mistake when I took my derivative or when I factored? So I feel like I really did something wrong here. Let's see. I got negative 12x squared minus 16x. That's looking good. I factored out. Oh, I did make a mistake. See, so here's what I want to kind of emphasize when you make, like, when something doesn't seem like it's working out, right? Like clearly I'm like, well, shoot, I know it's a minimum here, but I know it's supposed to be a maximum here, but I also know that it's supposed to be negative because of the value I was getting. I have to go back and look for where things went wrong. And things went wrong right here when I factored. I factored out the negative 4x, but I forgot to factor out the negative from here. So that should really be a plus, which means this whole sign chart's a little bit different. Because I got x equal to 0, and I should have gotten x equal to negative 4/3. So on my number line, it's going to actually be a 0 and a negative 4/3. So now if I pick a number larger than 0, like 1, negative times a positive is negative. Pick a number between, like negative 1, positive, positive. Pick a number very negative, like negative 10, positive, negative. So it's decreasing, increasing, decreasing. So I actually have a relative maximum at 0. And I actually have a relative minimum at negative 4/3. Sorry about that. If we plug in negative 4/3, let's go ahead and take a look. I know it's not pretty, but it's okay. Sometimes the numbers are not going to be nice. F of negative 4/3, it's going to be negative 4 times negative 4/3 cubed is negative 64 over 27. And then negative 8 times negative 4/3 squared, which is 16 over 9. And then plus 1. This turns out to be actually maybe a tiny bit less terrible, although you might not believe it. 4 times 64 is 256 over 27. Multiply this by 3 over 3 to get 48 times 8, I said was 384. Is that right? Yeah, it is. Over 27 plus 27 over 27. So this actually ends up being just slightly negative, right? 256 plus 27 is like 283. Yeah, minus 384 gives you negative 101 over 27. So negative 4-ish. Okay, that's not really important. So now we can fix our stuff. Oh, that means also my second derivative was incorrect, right? My second derivative should have been, oh no, my second derivative was still right because I looked at my unfactored form. So my second derivative is still good to go. So graphing this thing now, we've got the point 0, 1, and then here's negative 1. We know that we have, this is a relative maximum, right? Relative maximum right there at 0, 1, and then a relative minimum at negative 4/3, comma, negative 4-ish. So, sorry. Here we are at negative 4/3, negative number. So we're doing something like this. Minimum there, maximum there. There's my inflection point here at like negative 2/3. And here's my maximum. I don't love this problem because you can't really find the x-intercepts, right? There's no easy way to solve this equal to 0. It might be actually extremely, extremely hard to solve this equal to 0. And usually if someone's asking you to graph a thing, most of the time they're going to give you x values or a graph where you can actually find the x-intercepts. Not terrible, but you know, interesting. Let's do more graphing stuff. Let me graph some other graphing problems here. I got lots of graphing problems. Hiding from me somewhere. There we go. Yeah. Oh yeah, sure, of course. Here's the graph again. I knew it was going to look like this because our original function was a negative something cubed, right? It was negative 4x cubed minus 8x squared plus 1. So when you have a cubic graph, you know it has the usual cubic shape. And since it was a negative leading coefficient, I knew it was going to go, it was kind of the cubic shape reversed. It was going to go like this. I'll erase the other side as well. Look at that. So this is our typical process for graphing things. Intercepts, asymptotes, first derivative stuff, second derivative stuff. And hopefully the first and second derivative y values are not too terrible. Yeah. So I'm going to move on to another problem. If I can see it. Let's look at something, sure. It's always kind of how terrible do we want our numbers to be. Let's look at this one. Let's look at f of x equal to 3x to the 5th minus 5x cubed. Which again, due to being a polynomial, not going to have any asymptotes. So let's go y. And so these problems, again, these are in the context of graph it, find all the things. So y-intercept, x equals 0. You're also going to get y equal to 0. X-intercepts, here we can solve and find x-intercepts. If I set the whole thing equal to 0, 3x to the 5th minus 5x cubed equal to 0, I can factor out an x cubed. I'm left with a 3x squared minus 5. These are not going to be pretty, but we can actually find them. You're going to get x equal to 0. You're also going to get 3x squared minus 5 equal to 0, so 3x squared equal to 5. X squared equal to 5/3, x equal to plus or minus the square root of 5/3. Okay, let's find the first derivative stuff. My first derivative is 15x to the 4th minus 15x squared. Factor, or I guess set it equal to 0 to factor. This factors very nicely. We can factor out a 15x squared. We're left with an x squared minus 1 You could factor this further, or you can factor it as 15x squared times x minus 1 times x plus 1 equals 0. So we get 3 critical values, x equal to 0, 1, and negative 1. Pick a number larger than 1. 20. Positive, positive, positive. Now you can either keep picking numbers, which is what we've usually been doing, or you can say 1 came from this factor, x minus 1, with an odd multiplicity, so the sign's going to change. Or you can plug in 1/2 and say positive, negative, positive, the whole thing is negative. And then you can keep doing the same thing. You can either say 0 came from x squared, which has an even power, and the power is even, the sign stays the same. Or you can pick negative 1/2. Say negative 1/2 squared is positive, negative 1/2 minus 1 is negative, negative 1/2 plus 1 is positive, and a negative times a positive times a negative times a positive is negative. Finally, we're over here. Negative 1 came from this factor, odd power, sign changes. Or plug in negative 3. Positive, negative, negative, product is positive. So our function is increasing, decreasing, decreasing, increasing. So we have a relative maximum at x equal to negative 1. And the y value, we can plug in negative 1 and get 3 times negative 1 minus 5 times negative 1, which will be negative 3 plus 5. And then we have a relative minimum at x equal to positive 1. And the y value there would be 3 minus 5, which is negative 2. Okay, let's find the second derivative stuff. I will point out, because this happens a lot. When you find the first derivative, you want to factor it to be able to find the critical values and also to be able to evaluate where the first derivative is positive or negative. But then when you go back to finding the second derivative, you really want to use the unfactored form. Sorry, I was pointing the wrong thing. You want to use your unfactored form of the first derivative. It's going to be much, much easier to differentiate that than it is to differentiate this or this. I don't want to use the product rule when I can just take the derivative of that. So my first derivative is 15x to the fourth minus 15x squared. My second derivative is going to be, let's see, the 4 comes down, so 4 times 15 is 60. X to the 4 minus 1 is 3. Minus 2 times 15 is 30. X to the first. Factor, I can factor out of 30x. I'm left with a 2x squared minus 1. So I'm going to get x equal to 0. And I'm going to get, let's see. I'm going to get 2x squared equal to 1. X squared equal to 1/2. X equal to plus or minus the square root of 1/2. It's kind of gross. So I've got 3 critical values. 0, square root of 1/2, negative square root of 1/2. And again, I'm going to pick things over here in each spot. So pick something big like 5, positive, positive. Now, to me, it seems hard to pick something that's smaller than the square root of 1/2. But we can. We can pick something super small like 0.1. Square root of 1/2 is about like, I think 0.7. So 0.1 smaller. 30 times 0.1 is definitely positive. 2 times 0.1 squared minus 1. Well, 0.1 squared is small. 2 times a small number is still small. Small number minus 1 is going to be negative. So the positive times negative, so it's negative. Over on this side, it's going to be positive because you're now going to have a negative number that's small. So negative thing times 30 is negative. This part is also negative because it's a small thing minus 1, which is negative. So it's negative times negative, which is positive. And then finally, over here, pick something like negative 10. Negative, positive, makes a negative. So we have 3 inflection points. So we have an inflection point at x equal to 0, x equal to positive square root of 1/2, x equal to negative square root of 1/2. You could find the y values. For 0, it's easy. That's just the origin, because right, when you plug in 0, you get 0. When you plug in the square root of 1/2, let me find. So here's our function. F of x is, I forgot what it was already. It was like 3x to the fifth minus 5x cubed. Literally, it's on the other side of the board. Yep. So if you plug in the square root of 1, yeah, fine. So if you plug in the square root of 1/2, you get 3 times the square root of 1/2 to the fifth minus 5 times the square root of 1/2 cubed. I might actually factor it first. I'm going to factor it in kind of a very, very specific way. I'm going to factor out the x cubed. I'm going to write it as x times x squared times 3x squared minus 5. Right? That's what we factored it over here. We factored out x cubed. So now if I plug in the square root of 1/2, I get the square root of 1/2 times the square root of 1/2 squared is 1/2. And then 3 times the square root of 1/2 squared is 3 times 1/2 minus 5. I don't know if this is really better. It feels a little better. This is the square root of 1/2 times 1/2 times 3 halves minus 10 halves is negative 7 halves. I don't know. This feels kind of silly to me. This is going to be negative 7/4 times the square root of 1/2. It's gross. Often the inflection point y value is going to be gross. If I start going down this path and finding that the inflection point y value is like terrible, I usually stop and say, you know what? I probably don't need to do this. I'm just going to say, I know where it occurs on the graph, and then you'll see. So let's plot all the things. We have 0, 0. What else do we have? We have x-intercepts that were plus or minus the square root of 5/3, which is a little bit further out than plus or minus 1. So here's 1, here's negative 1, and here's my x-intercept that's definitely not as big as 2. Square root of 5/3, maybe it's about there. I don't really know. I'm just kind of guesstimating if I don't have the calculator. There's my negative square root of 5/3. And here's what I should have been saying last time, actually. After you've plotted whatever points and asymptotes you have, the first derivative sign chart is really telling you the shape of the graph. Our graph is increasing until we get to negative 1, decreasing after, decreasing after, and then increasing after. So we have the, oh, sorry, I should have plotted my critical values as well. I get negative 1, 2, and positive 1, negative 2. So here's what I know. I know my graph is increasing until I get to this point here, decreasing, decreasing, increasing. Now, I also know there's this weird kind of thing here because then I have an inflection point. So it's going to kind of flatten out for a second there and then kind of do this. So I have an inflection point there. And then I also have an inflection point like there-ish and there-ish. Right, where it's plus root 1/2 and minus root 1/2. There are lots of graphing tools at your disposal. I encourage you to use them whenever you're allowed to. Let's look at a couple more examples. Let's look at that one. We'll come back to you. What time? Okay, we got time. I want to do you. Sure. Let's do this one. Let's graph this function. It's going to be a little bit terrible. That's all right. They're all a little bit terrible. So you want to graph x squared minus 8 over x minus 2 squared. So this one is a rational function. We're definitely going to have asymptotes. Well, let's find the intercepts first. So y-intercept, x equals 0. Y is going to be 0 minus 8 over 0 minus 2 squared, which is negative 2. x-intercepts. For a rational function, you can just set the numerator equal to 0. You set x squared minus 8 equal to 0. You're going to get x equal to plus or minus the square root of 8. Or if you prefer, plus or minus 2 times the square root of 2. It's about 2.8. It's a little less than 3. Vertical asymptote, you're going to set with the denominator equal to 0. You're going to get x minus 2 squared equal to 0, so you're going to get x equal to 2. Horizontal asymptote, okay. Do we have a horizontal asymptote? Well, is the degree on top the same as the degree on the bottom? It is. The degree on top is 2. The degree on the bottom, if you multiply it out, is also degree 2. So the horizontal asymptote is the quotient of the leading coefficients. Right? If you multiply this out, you get 1x squared minus 8 over 1x squared minus 4x plus 4. Since the degrees are the same, the horizontal asymptote is the fraction of those leading coefficients. All right, we've done all of the usual stuff. Let's do the derivative stuff. So first derivative, gotta use the quotient rule. Sometimes so I've often asked this problem on a test and then actually giving people the first and second derivative because I want to test their graphing ability, not their derivative ability. But so that could be something that happens or not. So let's find the first derivative. It's going to be the bottom times the derivative of the top, which is 2x, minus the top, which is x squared minus 8, times the derivative of the bottom, which is 2 times x minus 2 to the first, times the derivative of the inside, which is 1. So it's just 2 times x minus 2 times 1. All divided by x minus 2 squared, x minus 2 to the fourth. All right, so typically, well, what you should notice here is that when we did the top part, so we had x minus 2 squared in the first thing that's being added or subtracted, and then we had 2 times x minus 2 to the first over here. We have x minus 2's in each part. We can factor some out. This is going to equal, and so I say, right, if you're trying to find the critical values, you have to simplify your derivative as much as possible. You have to factor as much as you can. I'm going to factor out an x minus 2 on top. I might as well also factor out a 2 since I've got a 2. So let's factor out a 2 times x minus 2. So let's see. After I factor out a 2 and an x minus 2, I'm left with still an x minus 2 times an x. And here I'm left with, let's see, I factor out an x minus 2 and a 2. So I'm left with a minus x squared minus 8. I can cancel this x minus 2 with one of these x minus 2's. So then I'm left with 2 times, let's see, x times x is x squared minus 2x minus x squared plus 8 all over x minus 2 cubed. So then simplifying the insides here, the x squareds cancel, and I get, I'm also going to factor out a negative 2. So you get 2 times negative 2 is negative 4 times x factor out the negative 2, so it's a minus 4 over x minus 2 cubed. Let me make sure that looks right. I feel like I made a mistake. Nope, I didn't. It's totally good. So then we're trying to find the critical values. So I will point out the only real critical value is x equal to 4, but x equal to 2 is still important to put on the number line for the first derivative. So x equals 4 is my only critical value, but x equal to 2 is what we call a pseudo-critical, or what I call a pseudo-critical value, or an important point. All right, so then pick a number larger than 4, like 5 if you want to be boring. And negative 4 times 1 over 3. So let's see, I really should say, if I pick 5, it's a negative times a positive times a positive. If I pick something between 2 and 4, like 3, it's a negative times a negative times a positive. Yes, I know I'm saying times when it's really divided, but multiplying or dividing, is, if you're only worrying about the sign, achieves the same result. Let's pick 1, or let's pick 0. Negative times a negative cubed is still negative, so negative is negative. So look, it was important to check at 2, because on one side of 2 it's positive, on one side of 2 it's negative. So my function is decreasing, increasing, decreasing. So we have a relative maximum at 4. We could find the y value. The y value would be blah. The y value would be, let's see, 4 squared is 16 minus 8 is 8 over 4 minus 2 is 2 squared is 4. So 8 over 4 is 2. Okay. We do not have a relative minimum at 2, right, because of a vertical asymptote. So what's happening at 2 is on the left, you're coming down to negative infinity, and then you're going up to positive infinity. Or sorry, you're coming up from negative infinity on the other side. So even though I haven't found the second derivative stuff quite yet, I'm going to start laying out the graph. I'm still going to find the second derivative stuff because we should, but here's what it's going to look like, kind of. So what have I got so far? A whole lot of trouble. So I've got a y-intercept of -2, I got x-intercepts at plus or minus almost 3. So there's my y-intercept of -2 here, my x-intercepts at almost 3, sorry, almost -3, and almost 3. I said I had a horizontal asymptote at 1 and a vertical asymptote at 2. And I also know the graph is going to be decreasing until I get to 2, increasing after 2, decreasing after 4. I also have the point 4 comma, no, yeah, that's right, 4 comma 2. So 1, 2, 3, 4 comma 2. All right, so here's what we know. We know the graph is going to be decreasing, so got to hit that point, got to hit that point, got to go down. After 2, we're going to be increasing at that point, hit that point, and then after 4, we're going to be decreasing again. So I'm pretty sure I know what this graph already looks like. It's decreasing. I'm also using the horizontal asymptote as a guide, right? I know I should be getting close to the horizontal asymptote, think about it that way. I got to hit that intercept, and then keep decreasing. After 2, I'm going to be increasing, still increasing until I get to 4, right? That's the point, 4 comma 2. And then after 4, now it's going to be hard to kind of see this because of where I do my graph. I'm going to smush this in just a little bit so we can see it a little bit better. Let's make that 4 there. I'm going to draw this a little lower than I really should. So after 4, then we're going to turn around because, well, it's a maximum. And then we have to get closer and closer to the horizontal asymptote there. So before we even find the second derivative, I'm going to guess that we have one inflection point. We have one inflection point somewhere after 4, right there, because it's concave down here, and then right about there, it looks like it starts being concave up. And that's kind of always happens when you have like a relative maximum or minimum, and then after that, you have to get close to an asymptote. You kind of have to change the direction that you're turning, right? Here, my car is driving and turning right, turning right, turning right, turning right, turning right, turning right, turning right. Then I have to, you can't keep turning right. If I keep turning right, I'm going to go back down like this and not level out to my horizontal asymptote. So I'm going to start turning left. All right. Unfortunately, finding the second derivative is kind of a giant pain. If you're finding the second derivative, you want to, no, that looks fine. So I'm going to take that, -4 times x minus 4 over x minus 2 cubed, and we're going to differentiate that. I would probably think of the -4 as being a coefficient out in front. So then I'm just going to leave that out in front. So my second derivative here is going to be -4 times the derivative of all this. So again, bottom, derivative of the top is 1 minus the top. The derivative of the bottom is 3 times x minus 2 squared times 1. All over the bottom squared, so x minus 2 to the 6th. So here we can factor out an x minus 2 squared from the top. So I do that. Just change pens. This pen's trying to destroy my pens. So let's see. If I factor out an x minus 2 squared, I'm left with an x minus 2 here minus a 3 times x minus 4 there. All over x minus 2 to the 6th. 2 of these cancel with 2 of those. And simplifying the top, so I'm going to do this kind of in one step because I'm tired of this problem. So let's see, I'm going to get x minus 3x, which is negative 2x. I'm going to get negative 2, and then minus 2 times minus 4 is plus 12. So negative 2 plus 12 is plus 10. So factoring out a negative 2, I get 8, right? Because negative 2 times 4 is negative 8, times x minus 5 over x minus 2 to the 4th. So here's my second derivative sign chart. My critical values for my second derivative are just 5. But we also know that 2 is an important, not actually critical value, but it's still important value. Pick a number larger than 5, like 6, positive, positive. Pick a number smaller than 5, or between, like 4, negative, positive. Pick a number over here, negative, negative, positive. So it's concave down, concave down, concave up. Just like our graph looks, right? Concave down, and then at the point here, 5 comma whatever, we have an inflection point. So there's an inflection point at 5 comma f of 5, which we could find if we plugged in 5 to the function. It's going to be 25 minus 8, which is 17, over 5 minus 2 cubed, which, sorry, 5 minus 2 squared, which is 3 squared, which is 9. Which is just a little bit smaller than 2, which it should be because you have a relative maximum right there. One thing I would like you all to observe from this problem, which I think is a useful piece of information. When you're differentiating a quotient like this, and the denominator is already raised to a power, every time you differentiate it, after you simplify, the power will have gotten bigger by exactly 1. So when we differentiated this and simplified, our power in the denominator went from x minus 2 squared to x minus 2 cubed. When we differentiated it again, and then simplified, our power ended up being x minus 2 to the 4th. If we did the derivative again, after we simplified, we'd get x minus 2 to the 5th in the bottom. I found that to be a useful pattern to recognize because it kind of helps me know if I've done things right or not. So I'm going to do one thing here. Okay, let me ask you guys. Do you want to do more graphs, or should I start talking about some optimization problems? And I guess I don't know how, but you could hit buttons, you could write things in the chat. How about a yes for graphs and a no for optimization? Using the things. You guys know what I'm talking about, right? You guys are like, no, I have no idea what's the reactions, right? You could use a green check if you want to see more graphs, or a red X if you want to see optimization. Oh. It's looking pretty even so far. I saw 3 X's and two green checks. All right, I'm going to talk more about optimization, or I'm going to start talking about optimization. But I will also say there's a lot of graphical context in optimization problems. So yeah, let's go optimization. Whoops, that's not what I meant to do. Close the one thing that I didn't mean to close. I mean, it's not hard to find, but like, good job. Okay. So optimization. There's a few things to say about optimization, but let's start with the problem. Here is the setup. People often start with like a fence problem. I feel like that always gets kind of a little bit boring. So let's do something a little bit different. So let's say we have an open top box. With a square base. Is to be made from surface area of 108 square feet. What is the most volume it can hold? Okay. So 9 times out of 10, when you're doing one of these optimization problems, you're typically going to need to draw a picture, or so there's going to need to be a picture. Maybe someone already drew it for you. Maybe you're going to draw it. So I have an open top box. So a box, right? Like a box. I've got like a million boxes in my garage. Go get one. Okay. Sure. Here's a Kleenex box. And if I orient it this way, right, the bottom, sorry, I can't see myself because I'm covered up here. The bottom has a square base, right? So I'm thinking of my box like this, except there's no top, right? It's open. So I can put stuff in it. So my open top box, I guess I'll draw like that, since why not? So there's my open top box. And it has a square base, meaning this dimension and this dimension should be the same. But the height is not the same as the dimensions of the base. So it's got a square base, and I know a couple things. In fact, I know two things. I know one, I want to have the most volume. So I want to maximize volume. Okay, so I need an equation for the volume based on the variables I've used in my picture. You might use different, right? You might use Z, Z, and X, or A, and B. But you want to use the least number of variables possible, meaning, right, if something is the same, you should give it the same variable name. And then we want an equation for the volume. So for a box, the volume is going to equal X times H. Okay, here's a really important tip. The thing you're trying to maximize or minimize, we don't know what it's equal to, right? I want the most volume. I don't know what the most volume is. This should not be equal to some number, right? We don't know what it is. We shouldn't be setting it equal to any particular number. It's a very common mistake for people to be like, oh, this equals 108. The second thing we need after the thing you're trying to maximize or minimize is the constraint. There is some physical limitation to our problem. In this case, the physical limitation is that we want the surface area, or other people might phrase it as the amount of material used to construct the box, to be 108 square feet. So our constraint here is that the surface area is equal to 108. But we need to get an equation for the surface area. For boxes, or anything that's kind of a rectangular three-dimensional object, it's just all of the rectangles added up together. So I might want to draw more of a picture. Right, so you can see that, okay, well, the bottom of the box has an area of X squared. So the surface area is the bottom area plus the front rectangle, which is X times H, plus the side rectangle, which is also X times H, plus the other side, which is also X times H, plus the back side, which is also X times H. And if it was a closed top box, or just a box, we would have another X squared for the top, but we don't because it's an open top box. So if someone says you have an open top, whatever, you don't have the top. We should definitely simplify this. We have X squared plus 1, 2, 3, 4 XHs equal to 108. So this is the beginning of our optimization problem. Find the thing you're trying to optimize. Find an equation for the thing you're trying to optimize, and then find a constraint. After that, the process is look at your constraint and try to isolate one of the variables. Usually, one of the variables is an obvious better choice. Here, I think we can all agree that it's much easier to solve for H. I can isolate H really easily. Solving for X would be really hard. In fact, if you wanted to solve this for X, you'd have to use the quadratic formula. You would get X equal to
negative 4h plus or minus the square root of some garbage all over 2. You don't want that. You don't want to solve for x. That way you want to solve for h. So I think I can erase my picture now. Yeah, I can erase my picture now. So the next step is to solve for a variable in constraint. In the constraint equation. So I'm going to solve for h because it's easier. Take the path of least resistance with rare exception. So 4xh equals 108 minus x squared. And then divide both sides by 4x. H equals 108 minus x squared divided by 4x. Okay, why would we do this? Because then we can plug this in to the thing you want to maximize. Because the problem here is if you're trying to maximize or minimize something, typically the way we find if a function has a maximum or a minimum is to take the derivative, set it equal to 0, find the critical values, and then test to see if it's a max or a min. The problem here is that your function you're trying to maximize is a function of 2 variables. And we only really have the ability to maximize things that are of 1 variable. So we're using this constraint to help eliminate a variable. So we're going to plug that in. And we're going to get the volume is equal to x squared times h, which is 108 minus x squared all over 4x. I think I've run out of room here, so I'm going to go to the other side of the board. So let's see. Again, I have volume is equal to x squared times h, which was 108 minus x squared over 4x. I can cancel an x here and x here. So I can say that volume equals x times 108 minus x squared over 4. And then I might rewrite this as 1/4 times 108x minus x cubed. Right, distributing the x and kind of pulling out the 1/4. Why would you do this? To make it easier to differentiate. Because now we're going to find the critical value. So we say, okay, v prime is 1/4 times the derivative of this, which is 108 minus 3x squared. And we're going to set that equal to 0. So I can factor out a 3. That's 1/4 times 3 times 36 minus x squared, which factors as 3/4 times 6 minus x times 6 plus x. Okay, so what are my critical values? Well, they're x equal to positive 6 and x equal to negative 6. So now we have to talk about context. One of these doesn't make sense. And I suppose maybe I erased my picture prematurely. And here's my picture again. X shouldn't be negative, right? That doesn't make sense at all. In fact, x should really be greater than or equal to 0. Maybe not even equal to 0. 0 seems like kind of a stretch. In fact, right, 0 is definitely a problem if you want the volume or the surface area to be 108. Right, the surface area is 108. You can't really have a x that's 0. And, well, yeah. You should also have the h is greater than 0. So this doesn't make sense. All right, so let's talk about the phrasing of the question here. The question specifically asks, what's the most volume it can hold? So we found x equal to 6 to be a critical value. Really, so I should say, I probably phrased the question I wrote. Usually the questions are phrased as what dimensions will maximize the volume, and that's probably what I should have asked. So what dimensions will maximize the volume, and then we can also find the volume. So what dimensions? Well, we got x equal to 6. We still need to find the height. Well, we know that the height can be found in terms of x. The height is equal to 108 minus x squared over, was it 4x? I think it was. It is. So the height here is equal to 108 minus 6 squared over 4 times 6. 4 times 6, not 46. 108 minus 36 is 72. 72 divided by 24 is 3. And then if you wanted to, you could find the actual volume. The volume would be, well, no, the volume. Sorry, this problem coincidentally happens to have the same volume as it does surface area, which is kind of annoying. The volume is 6 times 6 times 3, which is 108. That is purely coincidence. It is not anything other than a coincidence. The thing we should address here for just 1 second is, how do we know it's the maximum? Right? Is this really the maximum? Did I find where we have the most volume? So there's a couple things you can do here. You could, if you wanted to, use the second derivative test. And this is that. So I will say optimization problems are one of the places where it's sometimes more convenient to use the second derivative test. So I could say, well, the second derivative is equal to, let's see, the derivative of this is going to be 3/4 times the derivative of 36 minus x squared is negative 2x. And then if you plug in 6 for x, so v double prime of 6 is going to be 3/4 times negative 12, which I don't know what that, well, I do know what that number is, it's negative 9. And since our second derivative is negative, we do have a relative maximum. So what should I say about this? Sometimes, usually people care about asking you to show that the thing you found is actually a maximum or is actually a minimum, but it's probably less of a thing you can really be asked about via web work, right? Like, show it's a maximum. Well, okay. But you can either show it's a maximum by using the second derivative test, or you can use the first derivative test, right? We totally could, if we wanted to, on the number line for v prime, it's like, okay, here's our critical value, it's 6. And then also, we really should kind of limit ourselves to a meaningful domain, meaning x really shouldn't be any smaller than 0. Right, so we don't actually have the whole number line. So if we pick a number larger than 6 for our derivative, which I know is on the other side, okay, so I pick something like 7, 36 minus 7 squared is going to be negative. If I pick something like 1, 36 minus 1 squared is going to be positive. So we do have something that's increasing, decreasing, so it is going to be a relative maximum. It is important to check that the thing you found is actually the thing you want. Most of the time, if the problem says find a relative minimum and you found one critical value, it's going to be a relative minimum. Or if the problem says find a maximum and you found one critical value, it's going to be a maximum. Occasionally, there are some funky problems where you actually find multiple critical values and one of them gives you a maximum and gives you a min. That is less likely, but it's still something that can come up. Yeah, we got time. Let's do another problem. Let's do one more. So much like related rates problems, these optimization problems are all about the setup. It's your job to figure out how to set the problem up. So let's look at this problem. Let me make sure I'm writing it the right way. So a cookie company is selling. So a cookie, the Girl Scouts, could be the Girl Scouts. I guess they're not technically a cookie company. They're the ones who get you the goods. Cookie company is selling an average. So sells an average of 1,000 cookies per week. at a price, this price seems very low, a price of 30 cents per week. So $0.30 per week. Per cookie, sorry. We're selling 1,000 cookies per week at 30 cents per cookie. Okay. And the latest research shows that for every 2-cent increase, so a 2-cent increase in price or $0.02 increase, we are going to sell less cookies. We're going to sell 10 fewer cookies. 10 fewer, less, I don't know. I think fewer is the right word. I used to say like fewer when it's an actual number of things and less when it's like some not specific number amount. Yeah, that's English. So what price will maximize revenue? Because we're all about the dollars. Okay, we got 1 minute, we can make it happen. So we need to write an equation for the thing we want to maximize. So we're trying to maximize revenue. So revenue is equal to the number of cookies. So let's say that X equals the number of cookies sold, and P is the price. So that's going to be X times P. But we also know that the price depends on the number of cookies sold. Right, the price. So again, this is always right the part where it's kind of hard to make sure you make it work out right. I would say that. So the price of a cookie, we know it's 30 cents when the number of cookies is 1,000. How do you make this work out? So it's always kind of a problem. So I'm going to say the price is 30 cents. And then if X goes up by 10, if my price goes up by 2 cents, the number of cookies is going to go down by 10. I always have trouble setting this up personally. So let's see. I know that the price is negatively correlated to the number of cookies, right? So if the number of cookies goes up by 10, my price should go down by 2 cents. So I'm going to subtract 2 cents for when the number of cookies goes up by 10. So sorry. So here's what I think we're going to have to do. We're going to say that this is going to be so X is the number of cookies. Yeah, I'm sorry. My brain is like, there's a way to do this. This shouldn't be this hard. Let me take a look real quick here. Come on, brain. I feel like I'm setting this up in kind of a dumb way. Okay. Yeah, okay. That's what I should be doing. So the problem is that I kind of, I made the rookie mistake. I shouldn't have made a rookie mistake. I'm not a rookie. Of saying X was the number of cookies. So let's back that up a little bit. So X is going to, sorry. Let's say that the revenue is just the number of cookies times the price. Okay. X is going to be neither thing. So what we're going to say is, well, the number of cookies is going to be 1,000 minus 10x. So when X is 0, we're going to sell 1,000 cookies, and the price is going to be 30 cents. And then when X is 1, we're going to sell 1,000 minus 10 cookies, so 10 less cookies. And the price is going to go down by 1. Yeah. Right. Oh, sorry, less cookies means a higher price. Sorry. Price didn't go up by 1, so we're gonna have a 0.32. So the price would be 30 cents plus 2 cents times x. The problem with this kind of problem is, right, when one thing is increasing by a certain amount, the other thing is decreasing by a different amount, but still related on the same thing. You kind of want to use something like this. Say, okay, well, if x, right, if this goes down by 10, this needs to go up by 0.02. All right. So there's our revenue. Sorry, I know it's 10:23. If you need to go, feel free to go. I feel like I should finish the problem I started though. So here's the revenue. And notice this problem already kind of has the constraint built in, right? Maybe I kind of overlooked that, right? We could have said the revenue is a sentence and then figured out the constraint. I was kind of doing that all at once. So then we're going to differentiate. I would probably multiply this out first. This is going to be 0.3 times 1,000, so 300. 0.3 times 10x is minus 3x. 1,000 times 0.02x is going to be, let's see, 20x. And then minus 10x times 0.2x is going to be, 0.02x is going to be minus 0.2x squared. So we're going to take the derivative, which is going to be, I should probably simplify this a tiny bit, 300 minus 23x minus 0.2x squared. The derivative is going to be minus 23 minus 0.4x. And we're going to set that equal to 0. Solving for x, we're going to get 0.4x equal to 23. Sorry, equal to. Like, that doesn't look right. Sorry, it looks like I made an error somewhere. Sorry, this problem I feel like it's full of errors on my part. I apologize. Let me double check here. 300 minus 3 plus 20. Yeah. Sorry, guys. I feel like today I've made more errors than I usually make. Never my plan. Yeah, so 7. So sorry. So it should be 300 plus 17x minus 0.2x squared. The derivative is going to be 17 minus 0.4x. So we're solving 17 equal to 0.4x. Or x equal to 17 divided by 0.4. 17 divided by 0.4 is 17 divided by 4/10, which is 17 times 10/4, which is 170 over 4, which is going to be what, 85 over 2, which is 42.5. So x is the 42.5 to maximize this thing. So the question is, what price will maximize the revenue? Well, it's not x equal to 42.5. That's the price. It's the price is this right here. So it's going to be 30 cents plus 0.02 times 42.5, which ends up being, excuse me, sorry. Let's see, 0.02 times 42.5 is going to be 0.30 plus 0.02 times 42.5. 2 times 42 is 84.5. But the decimal is moved over twice, so it's, sorry, brain. Hmm. 0.0845. So it ends up being 38.5 cents approximately. Yeah. Oh, sorry, my brain missed the decimal spot there. That's, yeah. Not the best day for James. Sorry. There we go. And that's not 845, that's 85. So we get $1.15.